Hey there, welcome back. This is note video number 8, and it is on Sir Isaac Newton and his 3 laws. Well, who's Isaac Newton? Isaac Newton is this good-looking fella from history. He's known for lots of stuff, a lot of stuff. He was pretty awesome all around, and is widely considered by many to be the single most influential scientist of all time. I mean, that's a bold statement, to say that you have influenced science and thus humanity more, or I guess, I don't know if you can call it humanity, but like our understanding of the world in the universe, more than any other person. And there's been quite a few people over history. You're one, I'm one, everyone who came before you was one. So to say that you're the single most influential scientist of all time, that's a mantle to carry. So anyway, I, though, know absolutely nothing about him. I think I should put that on my reading list, or if there's a good podcast out there that talks about Isaac Newton and what he did, I think that would be interesting. But whenever that things like that happen, what you really want to know about the people who do these things is the process. Like what, when I talk about, when I mention, a little bit of history about him, I don't care about, the day he was born and, all of those really cold, facts and figures. They're all important to the story, but it's the story that's important. You're not just born and given a name, Sir Isaac Newton, and then, because you're called Sir Isaac Newton, we are going to, impart on you all of this knowledge that is just going to fall into your lap and in your brain, and you're going to wake up one day and be like, hey, everyone, guess what I just suddenly understand? No, there's struggle involved in all of this. And every single person that you learn about, there's struggle involved in their accomplishments. And that's what I think that we should learn more about, the struggle, than maybe even the discovery. Because it's just as important, I think, to kind of appreciating the whole system. So, Sir Isaac Newton, I'm going to try to figure out more about him. You start to learn about other people like Marie Curie, and some really interesting stories there. So, regardless, Newton's 3 laws. I'm going to do exactly the thing that I just told you, and without describing any of the struggle or how he figured it all out, we're just going to talk about what he accomplished. One of the things that makes Newton awesome in what he figured out, and why he is one of the most influential scientists of all time, if not the most influential scientist of all time, he figured out the orbits of the planets. So, if we talk about history a little bit of science, it was thought that the Earth was in the middle of the solar system. Not only the middle of the solar system, though, but the middle of the entire universe. That literally the entire universe revolved around the Earth. That is what people thought. People thought that, we were that important. It was kind of like without a whole... They found a lot of evidence that you could argue that made sense, but it was also a worldview that they wanted to try to find evidence to argue for. Humans wanted to be the most important things ever. So they would argue that, well, if you watch the sky, all of these stars, all these things that we track with preciseness, they all start at this end and they go to this end, and that would make sense if the Earth was in the center of everything. Everything is just going around the Earth. Like that, everyone can see that. You can't argue this. Why are you trying to argue that we're the center of everything? Well, as it turns out, we're not the center of everything. If you know anything about the structure of the solar system and the universe and everything else, we're not even close to the center of the entire universe. So, how did he go about doing this? Well, that's where the math gets interesting, and that's where he was such an amazing genius when it came to this. It's kind of understanding. Hold on, let's see what my next slide is here. Okay, so remember when we talked about physics, and one of the very first things that we learned was that it's all about the reference point. All right, so If your reference point is that you're stationary, remember how we talked about how important it was to have a stationary reference point? If your reference point is that you're stationary and that everything else is moving, we saw all those like different kind of spaceship questions, like you think you're not moving even though you are. And how that makes everything else look. Well, if you think that you're stationary and that everything else is moving, saying that you're in the middle of the universe and everything is going around you is perfectly logical. It's what you actually think is happening. Newton started to approach it from the standpoint of, what if we're not stationary? How would that look? What would it look like if we were moving? And is there any situation where we're moving and it looks like that we're seeing with our eyes? It would appear to be the same, but with us as a moving standpoint. And he started to explain the orbits of the planets this way, and how they're not perfect circles, that they're these ellipses. And if you've learned about ellipses in geometry, they're kind of like ovals. They go up, but they have two focal points. So at a certain distance, if you were to attach a string to the focal point and make a circular end, all right, so you have two spots. If you put like two pins in a paper and have a loop of string, and you put your pencil in the loop of string and draw an ellipse, so that the string is always touching one of the pins. You're going around in circles. That's what an ellipse is. So the sun is found at one of those focal points of all of the planets' orbits. So they have these long, elongated orbits, and the sun is always at the focal point. That's what he started to figure out. He started to show how this is going on, and people. It was funny. People were like, "No, that's way too complicated." They would look at his algebra. We'll say he was using algebra to do this, because that was pretty much the extent of math at the time, and algebra, geometry, trig, all that stuff. And they were like, "We can't follow your math, Newton. Newton, what you're trying to solve for is impossible. You can't, like, that would take such a high level." And he would do it, and they would be like, "No, we don't agree with you because we can't quite follow what you're doing." So you know what he did? He made advanced algebra easier. He designed a whole new way to do math to explain how he thought the planets moved. Because the other scientists of the time, all of the other scientists of the time, I mean, that's an exaggeration. That's what I don't really know about. But anyway, the mass disagreement was that it couldn't be shown with the math. So he invented a new kind of math to demonstrate what he was trying to explain to them. And we call that calculus. So when you get to calculus and you say that it's hard, remember, it was made to make advanced algebra easier. I find that funny. As part of all of this, though, he also figured out something else really interesting that most people don't know. He used math to predict, because remember, Newton was alive a long time ago. We didn't have satellites. We didn't have like geo-tracking anything. Your perspective was what you could see with your eyes from the surface. Like, there was, you weren't flying even on jets or, stuff like that. So anyway, he predicted that the Earth wasn't round like you all still think that it's round. The Earth is not a sphere. It's not like a perfect orb that's out there, flawless. It's not. It's called an oblate form. It looks like a beach ball that someone's sitting on. So it's bigger around the waist than it is the other direction. When you see pictures from space, though, it doesn't quite look like this, because remember, the atmosphere is still making a sphere because of the pull of gravity from the Earth's center on all of the gas particles. It would still make a sphere, but the land itself is squished a little bit there. So, interesting fun fact if you didn't know that about the Earth. Newton also came up with the theory of color. What's the theory of color, you ask? Well, the theory of color is, remember what theories are? We learned about theories and laws really early on. That was like the very first thing that we learned in this class. Remember, a law explains what happens in a certain situation. So that's, we're going to be talking about the laws of motion. But a theory, remember, a theory explains why something exists in the first place. Like, why does something do this? Why is this here? That's what theories explain. And neither one is any better than the other, but the theory of color explains why color exists. You know why color exists? Color exists because of different wavelengths of light. And if you didn't know this, you should. That the spectrum of light, the Roy G. Biv spectrum of light, exists because of energy, these like light energy, so sometimes they're photons like particles, sometimes it's like a pure energy, has wavelengths that have these forms of waves. So you can think of them like ocean waves. And the longer the wavelength is, the lower the amount of energy it has. So violet has more energy in it than red does. But it's our receptors in our eyes. We have these receptors in our eyes that get triggered on these different varying wavelengths of light, and our brain interprets those as colors. And these are the only ones that we can see. There's a lot more energy up here. There's every increasingly sized wavelength. It's still the same energy. We call them like radio waves, and infrared light is up here. And violet, if we get farther down here, we have like ultraviolet, and we get X-rays and gamma rays and stuff like that we think of as dangerous. But they're like, all of that stuff is in light. It's just high doses of it whenever you go to actually get an X-ray or something like that. But all of that stuff is kind of made, parts of our atmosphere actually filter off some of it. The ozone layer filters off things that are down in here, because some of these can become very, very, very dangerous, do bad things to your DNA. But anyway, so that's why color exists. Some creatures can see the next few wavelengths on them, like bees and things like that can see ultraviolet stuff down here. Some creatures can see wavelengths up here, like snakes can see things in like infrared, and sometimes creatures that hunt at night can see things in the infrared light. They actually see it as a color, but it's outside the range of what our biology is able to see. The receptors in the back of our eyes can't pick those up and tell our brains that they exist. It's a blind spot to our awareness. There we go. So that he was trying to solve, he invented calculus. But what we're going to talk about, and what most people remember Newton for, even though all those other things are amazingly important, plus the other 100 things that he did, are the 3 laws of motion. So, laws, remember, explain what you can expect to happen in any given situation. And guess what? That's where we get to do lots of math, because we can give you any situation and you can explain what will happen because of the laws. Law number 1, the law of inertia. The law of inertia states the law of inertia is an object's resistance to changing motion. So inertia means that you have an object, picture, I don't care, a block of concrete or a bowling ball or a piece of cotton candy, doesn't matter what it is. That object has the natural tendency to not want to change what it's doing. If it's sitting still, there will be a resistance to it starting to move. If it's already moving, there will be a resistance to it changing what it's doing, whether it be the direction that it's moving or the speed that it's moving at. There will be some type of a resistance there, and that's inertia. Inertia is that resistance to change when we're talking about motion. And the first law of motion is the law of inertia, and it states, an object at rest will stay at rest, while an object in motion will stay in motion until something else changes the system. So we have to think about all of these things as systems. We've talked about inputs and outputs and processes and all that stuff. When we talk about these systems, we're talking about all the different forces that exist in the different directions that they're going. You've seen me put a picture up on the screen before of an inclined plane with all these different arrows going on it. There was gravity pulling down and friction going back, and somebody pushing on the block going up, and there was another arrow on there that we called normal force. All of those are part of the system, and when they're all balanced, we've talked about this. When they're all balanced, there's no motion. Because nothing is going to change the situation, and inertia has resistance there. So there's nothing to overcome the inertia of what's actually happening. But if you have one of those arrows that you increase, then they don't all cancel each other out anymore, and you have a force in a certain direction, and that would then cause a change to the system. That would be an unbalanced force, so then change in motion can occur. Well, the law of inertia says that if there's never any change in that net force, if there's never any change in the input, then whatever motion is occurring will continue to occur until the end of time. That's pretty definitive. End of time is a really long time ago, a really long time away. To say that that will sit there, if nothing touches it, that it will never move, that's a really powerful statement. It is the first law of motion. It also says that if I throw a ball at you and it doesn't hit anything, that it will just keep going. But we know that doesn't work. We know that doesn't work because of friction. So remember, friction ends up messing a bunch of this stuff up when you think about it. So the most important law of inertia that we can use to illustrate here are how seatbelts work. So if you're driving down the road and suddenly the car stops because the car runs into something, well, your body is not the car. Your body is inside of the car. So your body is going to resist that stopping. It's not going to want to stop. It's going to want to keep moving. But the car stopped moving because it ran into something, so your body keeps going. That has to do with inertia. Your body is going to keep going until it runs into something, like the windshield. I don't know what kind of situation would cause this to occur, but it's not going to go well. So it is really important that whenever you are riding in a car, because you're all getting to be about that age where you're going to be riding in cars and driving cars, that you wear your seatbelts. Airbags are a really interesting invention. So the way both of these work, the way both seatbelts and airbags work, they don't stop you the way that you think that they do. If they did, they would not save your life. Think about it. If you're going down the road at 60 miles an hour and the car stops because it runs into something that's in front of you, like, I don't know, a tree, and the car's going to stop. There's no slowing down there. There's no like that gradual deceleration like a brake works. If you hit something, you go to zero. That is really, really rapid deceleration. That's like infinite deceleration. If you tried to graph that, that would be a straight up and down line. If you went to that speed at zero, if there was no give, you hit something that didn't give at all. Well, it's not going to save you if something is holding your body that doesn't have any give. If it would be like you hitting the wall yourself. Seatbelts work because they stretch. They don't work because they keep you from hitting the dashboard. I mean, that's really important that you stop before you reach the dashboard. That's why it's bad when the dashboard gets pushed towards you, because you reduce that distance that you have to get to the dashboard. But in the steering wheel, that really gets in the way. So what the seatbelts do is they stretch. They take that like moment of deceleration when the car has an accident, and they stretch it out through time. You have this like little bit of leeway to deal with the car, and the seatbelts are designed to stretch that moment out and slow down that deceleration, that rapid deceleration. I maybe should say speed it up, however you want to view that graph, because it's a negative acceleration. They stretch that out so that you don't reach zero so fast, and that's what saves your life. And airbags work the same way. Because that steering wheel is in the way, and now they have side airbags and airbags all over the place because they're just awesome, that when you hit that, it slows you down and kind of prevents you from smacking into the steering wheel. So at least when you do hit the steering wheel, you're not going so fast that it actually causes injury at that point because the speed has been lowered. So the physics behind how that stuff works is really interesting. So law number 2. So if an object that is sitting still is going to sit still forever, and if an object that's moving is going to move forever, as long as friction and things like that don't exist, law number 2 says that when you have overcome inertia, when you have you're putting force on an object, when you don't have balanced forces anymore, when there is an imbalanced force and a net force is actually being applied to an object, what will happen? And what will happen is it'll start to move, or it'll move in a different direction. And remember, anytime we change velocity, or anytime that we are moving faster or slower, we call this acceleration. And how much something accelerates depends on the force that is being pushed on it and the mass of the object. So all of this time before now, when we're talking about free fall, and we're talking about how fast something falls, and I've said, it doesn't matter how much something weighs, it doesn't matter what the mass of the object is, all things fall at the same rate. And that doesn't jive well with the way that some people think of the world. Some people want heavier things to fall faster. It's just simply, though, not the way that it works. You have this misconception because of the way feathers and things like that catch the wind and kind of ride the air down because of their surface area. They can do things like that. But what happens when we start talking about this is where the mass starts to count. It doesn't count when we're talking about things falling, but it does count when we're talking about how fast things, or how much force things have when they run into you. Or if you want to change something's direction, how much force do you need to apply to it to do that? And mass has a great deal to do with that. I mean, think about this. Think about if you take the biggest person that you've ever met, not even the biggest person in class, the biggest person in school, the biggest person you've ever met, and take then the smallest person that you've ever met that could still run, and have the biggest person they've ever met just stand there, and the smallest person run into them. They're going to hit them with a decent amount of force. You get up a barrel of steam and just take off running and run into somebody. But if they're running into somebody that's so big, it's not going to have as much of an impact. They're going to be like, hey, how you doing? But if that big person pushed on the little person with the same amount of force that they were just hit with, that little person would go flying backwards. It's the same amount of force, but it depends on who is pushing and who is receiving about what actually happens in the real world. And you're going to see this applied here a few times moving ahead. So our equation, and this, I would argue, is the most famous equation in physics. When we came into class, I may have asked you what you thought the most famous equation was in physics. And most people, if you say, give me a physics equation, would say something like E equals mc squared. But very few people can actually tell you what this means and what the different parts of it stand for. And I can guarantee that even fewer, even if somebody knew what C stood for, or knew even what E stood for that matter, or knew what to do with a square root, with a square sign, very, very even fewer people have ever actually used this equation to solve a problem. Because that's just not something that we ever do. We never really use this formula to solve any kind of physics problems unless you're doing some pretty high level physics. But this is a formula that just doesn't get used in physics classrooms very much. It's famous. Einstein said it, and we figured out really cool stuff because of it, and we can use this formula to justify lots of the ways that we think the world works. It's just not one that we actually work the math out for. Well, and I'm sure there's going to be lots of people with high-level physics that would disagree with that. But this formula, the one on this page, right here, you could talk to every person that has ever taken physics in high school and said, do you remember the formula F equals ma? And a light bulb will probably go off, and they'll be like, yes, that's actually the only thing that I remember from physics is F equals ma. This is probably, I think, the most famous formula in physics. And a lot of it has to do with maybe because some of the things that you can figure out with it are also fun and make sense. And we're back to things that make sense because you can actually kind of imagine yourself pushing on something, or imagine what this force would feel like. That acceleration stuff is a little bit tricky because you don't know what acceleration feels like. Well, maybe some of these problems will actually help with that as well. So, the equation F equals ma stands for force equals mass times acceleration. And remember, we can do some algebraic gymnastics and flip things around, and we can also solve for acceleration. We could also solve for mass. It's free-flowing. I said in an earlier note video that I was going to go back to the free fall acceleration ones and show you how you can flip all those around. It would be interesting if you go back and look at those. They're all one formula. All three of those acceleration formulas that we used to talk about before are one formula. You can use substitution, as you learned how to do in algebra, and turn one into the other. It's just that those are the three most useful ways to break them all apart. And I'm not going to torture you enough to make you figure out how to turn one into the other. But it's an interesting thing to know. They're not three separate formulas. It's just the way that acceleration works. There's one law that kind of says what it is, and this is the way that the math works out, and we've just broken into three different ways to do the problem. But anyway, got off topic, my bad. Let's talk about that. So how much force is needed to give a 1 kilogram mass an acceleration of 1 meter per second squared? Again, this is the thing that you have a hard time imagining, an acceleration. What does that feel like? Well, you can imagine what a 1 kilogram mass would feel like. That's 2.2 pounds, so a 2-pound bag or whatever. How much force would you have to push on that 2-pound bag or whatever to make it accelerate at that rate? Well, force is mass times acceleration, so that means it would be a 1 kilogram object going at an acceleration of 1 meter per second squared. The force would then be 1 kilogram meter per second squared. This is when they start to get a little wild. This is your unit. This is your unit of force. Whenever we start doing math and you finish with a unit that looks like this is a force. So just like any unit of distance would be a meter. Any unit of time might be like a second. If we put them together with a meter per second, we talk about a speed. If we have another second in there, we make it second squared, we have an acceleration. Well, now we've added the mass. Now we're talking about the mass and how the mass plays into this whole physical thing. And we have a kilogram. My G just ran off the screen. We have a kilogram meter per second squared. And that is what we call a Newton. A Newton is the unit of force that we have assigned that it takes to take a 1 kilogram object, a 2.2 pound object, and make it move with an acceleration of 1 meter per second squared. It's kind of arbitrary, but still based on all the SI systems, like that everything's kind of based on the kilogram, everything's based on the meter, everything's based on the second. So it is the most emblematic force that you can have. So that's where we start. That's what we measure everything for. That's the standard. And it's roughly a little less than a quarter of a pound worth of force, if you think of it in American terms. So what do these forces feel like? Well, let's say that you're benching and you're going to bench press 100 pounds. Well, 100 pounds, well, we do a little bit of a conversion here. 100 pounds, there's 2.2 pounds in a kilogram, so that would be equal to 45 kilograms of mass. Well, what would the acceleration be? For this case, we can just use the acceleration of gravity if you're going to be pushing it straight up and down. And it would be about 450 newtons of force. Which, hey, that makes sense. Because if a newton is a quarter of a pound, or a little less than a quarter of a pound, 100 pounds of bench pressing would take a little bit more than 4 times in the newtons. So, if you remember how these things you start to equate to each other and what they feel like, some of those answers will make more sense. So here we have the regatta. Pittsburgh is really known for its regatta. Let's say we have a speedboat on the Allegheny during the regatta, and it's pulling a 55 kilogram water skier. Remember, 55 kilograms, that's a little bit more than 110 pounds. The force causes the skier to accelerate at 2 meters per second squared. That's the same acceleration that we had Mr. Wood on the track going. What is the net force that is causing this acceleration? Well, we know that she's not going to accelerate for 800 yards. She'd be going like 130 miles an hour. But for this moment of acceleration, this moment that changed her speed, how much force would that boat need to use? Well, if we have the mass of the skier of 55 kilograms, the amount of extra force that we would need to pull it at 2 meters per second squared. F equals ma. Force is mass times acceleration. 55 times 2.0 gives us 110 newtons, or 110 kilogram meter per second squared. A couple real quick ones. What is the net force on a 1,000 kilogram object accelerating at 3 meters per second squared? This is just substitution. Put the numbers in. Let the math do it for you. So 1,000 kilograms at 3 meters per second squared is 3,000 newtons. What force is needed to accelerate a 25 kilogram cart to 14 meters per second squared? Just multiplication. So this is kind of done here to show you that the math isn't hard. The hard part is when you're given a situation, like comprehending the situation and thinking about a real situation in scientific terms, in a scientific way, and then sticking that realization into the math problem. So I've always said it's students who have a hard time with some of this, it's not because you can't do the math, it's because it's hard to figure out what math to do. Like, that's the real science behind it. The math is a tool, you just need to be able to do the math. All right, so here's an actual situation. We'll take some of that genericness out and actually apply it to something that's real. A professional hockey player strikes a 0.15 kilogram puck, that's the actual mass of a puck, with a force of 1.8 newtons. What's the acceleration of the puck? So that's actually not a whole lot of force if you think about how much a newton is. Well, F equals ma. This is where we have to rearrange it a little bit because we're solving for acceleration. We have the mass of the puck, we have the acceleration. I'm sorry, we have the mass of the puck, we have the force, solving for acceleration. 1.8 kilogram meter per second squared. Remember, that's a newton. That whole thing there is the newton. It's going to be important that you're able to do that to solve for the different things. And then divide that by 0.15 kilograms. The kilograms cancels out, and you're left with meters per second squared. So you're left with a unit of acceleration. You know you've done it right. And it'd be 12 meters per second squared. Now, you could then go on and figure out how fast the puck was going when it actually got to the net if you knew how long it took the puck to get there. So what's interesting about that is it doesn't take a whole lot of force to move that thing really fast. And then it ends up slowing down with like friction and all that other stuff. But you get that stick whipping. It doesn't have to be a real heavy stick to get that thing flying. All right, here I have Mr. Reagle's car. Ooh, this is a quick check. So you're going to have to think about how to solve this one. Mr. Reagle's car weighs 3,000 pounds. That's legit. These are all real numbers, by the way. Weighs 3,000 pounds and can reach a speed of 60 miles an hour in 4.5 seconds. So how much force is the engine creating to pull the car? So here's a picture of the engine on my car. How much force is able to be created in this motor in order to make the 3,000 car hit 60 miles an hour from a stop in 4.5 seconds? And then when we start learning about power next, because after force we learn about work, and then after work we learn about power. And once we get to the end and learn about power, we're actually going to use starting with this problem. And this is the we actually got this information, this 60 miles an hour in 4.5 seconds from an earlier problem where we compared the speed of the motorcycle to the speed of the car. So these are all the same numbers that we just keep using. Once we get to power, though, we're going to learn about the horsepower. So we're going to see how you could actually take, if you know how fast you go in a certain amount of time, you could take that all the way up to calculating the horsepower of your engine. So to solve this particular small part of this long problem that we're doing over the whole 9 weeks, if the car weighs 3,000 pounds, you can reach the speed of 60 miles an hour in 4.5 seconds, how much force is the engine creating? So what kind of things, you have to kind of think about your strategy. What's your math combat skills here? So we're talking about force and mass and acceleration, so it's a pretty good bet that you're going to be needing this one, especially since we're asking for force. So the force is in the sentence with the question mark. We're solving for force. Hey, it's already in front of the equal sign. We don't even have to do any gymnastics. Sweet, that makes it easy. So do we have a mass? Well, we have a weight, and you could do some converting. Do we have an acceleration? We're not given an acceleration. We're given a top speed. We're given a final velocity, and we're given a time. Huh. I don't seem like I'm given everything that I need. I'm trying to solve for force, and I can get the mass. I can do that. But how do I get acceleration from these two numbers here? Well, there is a way. You have to go back and use all of that stuff that we've been learning. So let's plot out a little bit of a strategy and then see if you can enact it. So first, you have to know the mass in the SI system. Remember, in order for it to be in Newton, in order for you to answer this answer with force in newtons, it must be in kilograms. So if I give you something in grams, make sure that you always put the mass into kilograms. That is really vital. Those units are vital. So first, what's the mass of the car in kilograms? We need that. What's the final velocity in meters per second? Well, we know it in miles per hour, but we'll have to convert that into meters per second. What's the acceleration in SI? This is going to be the tricky one. The secret is we just learned how to do that. Look, it's an acceleration. Oh, we're solving for acceleration and we have some variables. It's probably going to be one of those three formulas we learned to use. So once you have acceleration and you have the mass and you have all of that other stuff, then you can solve for force. This is an example of like a 5-step physics problem, but you can do all of these steps. You just have to think about what order that you need things and what information do you need to be able to pull out. So you have 3 numbers up here and you can solve all the way down through to force. Do a little science with the right arm and a little math with the left arm. We'll join some math and science together. It's what we call physics. All right, the third and final Newton's law. This is the law of equals and opposites. And to paraphrase, it says, for every action there is an equal and opposite reaction. Some people can say that you can do that in society. Some people say you do that in politics. Well, you definitely do it in physics. Every time one side does one thing, the other side will do the opposite. This gets really interesting and kind of intriguing and sort of challenges the way that you think the world works. And I think, though, that it's the things that we learn about that challenge the way that you thought the world worked that makes learning about science interesting. So, the implication of Newton's third law. It explains lots of things. Let me get a little whiteboard here. Let's say that you are standing on a table. And here you have a really short upper body. Give you an arm. Yeah, that's a great picture. Yeah, go. That's why I don't teach. That is why I don't teach art. My arms and legs and knees and everything are all going everywhere. Let's say we'll go with a stick figure. That'll work. Let's say you're standing on a table. Well, you have a mass. You have a mass of, we'll say, X kilograms. And gravity is pulling you down with the acceleration of 10 meters per second squared. So you have a certain amount of force that you're putting on the table. But you're not moving. So if you're not moving, you're not accelerating. Your velocity is not changing. The first law of motion is kicking in because you're stationary. You are standing still. Nothing is overpowering your inertia. But you still have this force of gravity pulling down on you. You are still applying a force to the table. The only thing that would explain why you're not moving, the only thing that would explain why you're not crumpling into the ground is if this table was pushing back up on you. You're pushing on the table. The table's not moving. You're not moving. The only thing that would explain that is if there was an equal and opposite force that was pushing back up on you. Well, if that's the way the world works, that has some really interesting implications. One of them is it explains why we jump. Think about this. Think about, before we go on, if you had to explain to someone how jumping worked, how would you explain it to them? Like if you had to break jumping down into its core science, how does jumping work? Use your muscles, tense up your muscles, push against the ground with such force that you throw your body up in the air. Let me ask you this. Have you ever tried to lift yourself up in the air? Try it. Lift yourself up in the air. We would call that levitating. You're like, Mr. Reagle, you're a moron. You can't lift yourself up in the air. You can't float. Well, it's kind of what you're trying to say if you say that you're using your leg muscles to push yourself up in the air, that you're lifting yourself up in the air. A little bit. Because what really happens when you jump is that you use those leg muscles to push into the planet. Like let's say let's remove the table from the equation. Now you're standing on the ground. You're standing on the ground. You push down really hard with your legs. You are applying force to the planet. The planet has a really big mass. So if it's F equals ma, you are applying this force to an object with a huge mass. To get that mass to move at any new acceleration would require a ridiculous amount of force. So the planet doesn't move. The planet doesn't move when you push on it really hard. But what the planet does do is the planet pushes back. The planet pushes back with a force that is the same that you pushed on the planet with. Well, a really large object pushing on you with any amount of force, more than it doesn't already, is going to cause you to have an acceleration. Because the mass is kind of changing in the equation. It's not a straight line thing, because whenever you do, just so I don't create any misconceptions here, whenever you do the formula for F equals m, oops, write it down here, to do the formula for F equals ma, and you want to know the amount of force that you are pushing on the planet with, well, that's your mass. So if you rearrange all that, if the acceleration was actually equal to F over m, this is your mass. It's your force divided by your mass to figure out the acceleration. Well, when the planet pushes back, it's the planet's mass. You're going to create a lot more of an acceleration, even though the force is the same. So the planet actually throws you into the air when you try to jump. You push down, the planet pushes back. The stronger you push down, the stronger the planet pushes back. Then you can get to the point that you can jump really high and compete in the Olympics and dunk basketballs. Do lots of awesome things. You can jump really high. We're going to actually calculate in the next 9 weeks how much force one of your muscles has to create in order to make you jump high enough to dunk a basketball. There's a lot of simple machines involved, and levers and joints and things like that in your legs that we have to kind of factor in whenever we figure it out. It's one of those long, complicated, many-step math problems. You'll love it. So, how does walking work with this? Because walking is also completely controlled by the law of equal and opposite directions. Well, you move forward when you walk because you push backwards with your feet. Think about the actual mechanics of walking. Put your foot on the ground and go to take a step. Well, you actually pull back on your foot. Your foot is kind of stuck to the ground. That's friction. You pull back on your foot and it makes the rest of your body go forward. Well, the amount of force that you pull back on your foot turns into a forward opposite force for the rest of your body. There's an equal and opposite action going on. And we have equal and opposites here between hit the button, between the weight pulling you down and that normal force pushing you up, because you're not going down or up, you're going forward. So that part of it is all balanced. Well, it makes it really hard then to walk on ice or things with very low friction, if we got real and stop talking about worlds without frictions, that if you take the friction away, if you're living in that world, that you try to pull backwards with your foot, but there's nothing that is, your foot's just going to go backwards. You can't make the rest of your body go forward. Think about that for a minute. If I dropped you in the middle of a floor, and it was an actual frictionless floor, which remember cannot exist, that's physically impossible based on everything that I know about physics anyway. All the work that's ever done is to try to reduce friction and make it as small as possible, but you can't quite ever get to zero because you're always going to be rubbing up against something unless it's a complete vacuum. But let's say I dropped you in the middle of a room that had a frictionless floor. You would not be able to move. You would be trapped in the middle of that room. You would not be able to work your way to any of the walls. You would not be able to progress any direction. You could sit there and flail and flop around, but you wouldn't actually ever be able to move. You wouldn't be able to get anywhere. That would be crazy and terrifying and horrifying and everything else. I mean, talk about, it could be as big as you want, but your world would be completely claustrophobic. You wouldn't be able to move if there was no friction. So sometimes we get too caught up into talking about how friction is the enemy when we start talking about machines and how the more friction you have, the less efficiency there is. And you try to reduce all this friction, but friction itself is pretty important. So here's an actual problem with Newton's third law. So for every action, there's an equal and opposite reaction. So this is more of a thought problem instead of a math problem. You drop a basketball. It hits the ground with a certain force. Based on Newton's third law, an equal amount of force pushes the ball back up in the air. It falls back down to the ground again. Hits the ground, bounces back up in the air. Falls down, hits the ground, bounces back up in the air. Well, if every collision resulted in an equal and opposite reaction, then that would mean that the ball should keep bouncing back up to the height that you dropped it from. Think about the stuff that we've learned about with potential and kinetic energy. If you're up here with this level of potential energy, and you start to fall and you build up kinetic energy, and when you get down here, you are maximum kinetic energy and zero potential energy anymore. Well, if you hit the ground, there's going to be a level of force involved there, depending on your mass and what you're accelerated, like how fast you were going and whatnot. You're going to hit the ground, and the ground's going to throw you back up. Well, you should, all of that energy, because remember, you can't destroy energy, and you can just turn it into different forms. If all of that energy was then equally pushed back up, you should go back up to where you started. And then you'd fall back down again, and it would be endless. You would never stop bouncing. That's what would happen if this law were true. So sometimes we learn things in physics, and you're like, this just doesn't make sense. Why doesn't that happen? Like, that's not the way the world works. But the world doesn't work that way because of friction. Friction gets in the way. So friction is vital, but this is the way that it interferes with the way that we explain how some of these laws work. There's friction that exists everywhere there. So when we were doing all the projectile and free fall problems, we ignore all the air friction because it does make things really complicated as far as to try to actually predict the future with math. You have friction with all of the air molecules that you would be rubbing up against. There's internal friction of the material itself. When that rubber flexes when it hits the ground, the molecules in the rubber, in the material itself, slide around each other, and there's internal friction. The sliding creates its own amount of friction, which then robs some of that energy, some of that kinetic energy that is built up from it falling. From that potential energy turns into the kinetic energy. Some of that energy gets lost because of that friction. So there's not as much of it when it actually collides. It's lost, so the Earth doesn't actually push up with as much as it was actually struck by, because it just all kind of dissipates out to the variety of frictions that you experience in the environment. If friction were zero in everything, not just with the ground, but inside the material and all that stuff, the ball would bounce forever. What's a really interesting implication of all of this? Whenever we talk about, earlier on we talked about physics, and we talked about the different forms of energy, and how you have that potential energy, which is based on location. How high the ball is the easiest example. And you talk about kinetic energy, which is the energy involved in motion. And we've talked about how temperature is just a form of kinetic energy. It's the motion of molecules, and it's the speed at which they're moving and the speed at which they're vibrating that we feel as heat. So if you think about this, you could, based on this law, if I had a room, let's say the room was like sealed up, so it was its own system, and I suspended 10,000 bouncy balls from the ceiling. We can pretend that it's like the room at the science center that the little kids can go in and they throw all the balls up in the roof, and then a bell rings and the door opens up and all the balls fall in. Imagine if we had 10,000 of those in the classroom, the ceiling of the classroom. And the bell rings and the roof opens up and all these balls start bouncing around. Well, they're not going to bounce forever because of friction. There's a really interesting video that shows that I used to show in class. It was like a commercial for a color television, and they had all these different colored bouncy balls bouncing down like a street, like over in like Italy. It was kind of cool to see. So imagine that happening. They're bouncing all over the room. If there's no friction, they would bounce forever. But there's friction, so that energy gets lost. Well, you can't destroy energy, so what does it turn into? It's an interesting thought. Where does it go? Well, do the bouncy balls glow? No, it's not like every time they hit the ground and that energy gets lost, there's a burst of light. That would be cool. It's not what happens. So the energy is not turning into light. Remember, that energy has to turn into something. Well, most often when this question is asked, most often when energy is lost, the answer is heat. So the friction causes inefficiencies with the way that this law functions, and you lose the energy, so it's not quite the same energy that's being given back in to make the ball bounce up to the same height that it was dropped from. That energy gets turned into heat. You could actually calculate, if you knew enough information, if you knew the material that the balls were made out of, and you knew its elastic qualities, and you could calculate how much the temperature in the room would rise based on dropping 10,000 bouncy balls into the room. That's cool. That's a really cool, monumental cause and effect. That's just neat, the things that you could figure out with physics. All right, so if this bounce past basketball hit the floor at 30 degrees, what would the degrees that it would come back up off the ground with be? Yay, 30 degrees. Equal and opposite. Booby trap, 13 questions. Good luck. Newton's 3 laws. Don't forget to do the exit slip.